Welcome back. Welcome to another day of 115. Sorry if it took me a few minutes to get started up. For whatever reason, YouTube decided it did not want to allow the stream to begin today. Sometimes it be like that. So what we're going to be talking about today is using some of these cryptographic libraries, both on the JavaScript and Python side. One important thing, and I realize I'm about to lose about every viewer I have. So we're going to talk about this today. Hopefully you find it interesting. Hopefully you find it enjoyable. And it is useful as far as, actually creating any sort of actually understanding how all of these things work. For this course, we are not expecting you and will not ever require you to actually write any of the code that I'm going to be going over. Getting all of these details correct is actually really, really tricky. And even beyond that, and I'll talk about this during the live Q&A, and hopefully if you have questions, I can answer them. One of the things you're going to discover is the way that I have this application set up isn't actually all that secure, to be perfectly honest. It's not the best security. It's a good way of showing how we can write this public key cryptography and use the public key cryptographic libraries. But actually writing a secure application is incredibly tricky. There are lots of really finicky details you have to get correct in order to make it truly secure. And so a lot of this is just beyond what we can do in this course. So a few things just to start out, right? So what we're going to be talking about today, if the title of the video did not give this away, is we're going to be using the sort of chat app 2.0. So we're going to take that chat app where you could send messages and receive messages, and we're just going to add a little bit of, we're going to use encryption inside of it. We're not actually going to make it any more secure, to be perfectly honest, because when we send all of the information we send from the server back to the client is going to be in plain text, simply because it doesn't make for as interesting an example. And there are other issues with how we're going about this. But the idea, again, is to give you an idea and let you see how these libraries work, understand how you could use them, talk about best practices. But if you really wanted to make a secure application, the first thing you need to do is have a lot more experience in this. There are a lot of really big mistakes. So as far as the HTML goes, the HTML isn't all that new or different. You can see here, right? So the big thing is that we're going to have, our ajax.js to be able to make, that has our functions for post requests and get requests. We have another file, I called it HTML manipulation, htmlmanip.js. This just has some of the functions that I keep rewriting that handle some of my, some of the HTML manipulations in the JavaScript side. So one is that get contents in clear, that gets the contents of a text box. So a input element, right? So we're going to get that element. We'll get its value, that is the contents that it has, set its value to the empty string, so we clear it out so the user knows that their message went through, and then return whatever text we got. I also have something, because I realized I was writing this over and over again, display contents in HTML. So it takes in an element ID, a string, and an array. And what it's going to do is go through each string inside that array and add it to our accumulator. Afterward, it'll add a breakpoint, a new line, and then update the element ID. This will be a div, so we're going to use its inner HTML key, but set that to the accumulator, just so we can display whatever HTML that we have. Howdy, missed you too. Though the fact that you said howdy still amuses me. So hopefully that part's still very similar. We're going to have our front end. This will be the JavaScript. I'll show you this in a little bit to talk about how this works. We're just going to have, as far as the HTML goes, we'll have an area saying send message. And what we're going to do is we're going to have a input box for the text we want to send. And then we'll have two different buttons, the send unencrypted button, which we'll call our send plain text message function, and send encrypted button, which sends an encrypted message. So two different ways we can send the message, and we'll display them separately just in those two areas. The big thing to note is I have a new library that I am loading in here. It's really long and complicated, this URL. I'm not going to read it out. What this is as you can see by the name, the NodeForge library for JavaScript. This is a very, very popular library, a very powerful library that we can use to add encryption into our program. One mistake that lots of people like to make is writing their own encryption algorithms. And now it is something that is good. It can be very useful. It can be a lot of fun. I've actually done it in my life. But as far as security goes, it's not always the best bet. The number of different ways and the number of ways that people can attack an encryption algorithm is just incredible. The amount of mathematics and actually physics, chemistry, whatever you want to call it, entropy, all these details that are needed is just insane. And so while it is fun to make them, and I certainly encourage you to, like I said, I actually have an algorithm, a way of doing secret sharing to my name. If you really want security, it's best to leave it to some of these larger projects where people have really gone through all of the mathematical rigor to prove that they are going to work. But for now, for a project like this, just have fun. So as far as our front end goes, a couple of functions. We're going to have this get key. So we're going to be using public key cryptography. So remember, that's where we create two keys, a public key, and that's what we use to encrypt a message. And then the private key, which will be kept private, is what we use to decrypt the message. So when our application starts on the website, we're going to have to make two requests. I have two functions. If you look in the index.html, I have code here to call both functions. The first thing that we're going to do, front end, is called get key. And this is just going to make a request for that public key so that we can encrypt traffic to the server. The second thing that we're going to call is get messages, and that'll just send us a list of those messages back. So the get messages is pretty simple. It's display contents here. I'll show you, I'll put in the log what we receive. Of course, it'll be a JSON blob, so I'll have to convert that JSON blob to usable JavaScript data. And then it'll be an object. It has two keys, public and private, both of which are just arrays of strings. I'll display the contents of each of the arrays in the appropriate place. The much more interesting code is going to be everything else that we have to do. So just to start, when we get the public key, that's actually relatively simple. What's going to happen is, again, we're going to get a JSON blob. So we have to convert that to usable JavaScript data. The big thing in this object that we get back will be this key. And what we're going to be sent is honestly a large amount of, and you'll see it in a little bit, really unintelligible characters. It's honestly the way what we're using this public key cryptography. We're actually using an algorithm called RSA. This stands for the initials of the three people who originally developed it, Revest, Shamir, and Edelman. This was back in 1978. This is actually the paper that came up with this algorithm. Actually involves, that paper was the one where we came up with the idea of Alice sending a message to Bob with Eve trying to spy on them. It's a very big paper. The trick about RSA encryption is what it is based off of are two incredibly huge prime numbers. Actually, it could be based off of any two prime numbers, but obviously if you choose like 2 and 3, breaking that algorithm will not be too difficult, breaking that message. So we tend to use very, very large numbers because it makes it harder to crack. So what we're going to be getting is a encoded way of storing this huge prime number. And so what we're going to do is the actual content we get back, that this message is not going to be very interesting. What we have to do is create the public key from that. And so to do that, we're going to use that Forge library.pki and then .public key from PEM. And PEM is it's a type of file, just sort of like .db. It doesn't have to be named .pem, but they usually are. So it's standard that we use to share public keys. So we calling this function, it's going to return our public key. Then what we have up here is where we're going to use that is in our encrypt message. So when we want to send a plain text message, we'll get the contents of that box, create an object just for the plain text. I used an object. I have a key here in case we wanted to be able to send encrypted messages back and forth. But honestly, when I was timing out this lecture, that made this video too long and didn't add anything interesting. But I have it here for the future. At some point, I'll probably add that. Convert that object to JSON blob, send it out. That part's sort of like before. For an encrypted message, we're going to do the same basic starting point to create our plain text, right? Plain text is the term that we use for the text that we want to send when it's unencrypted. But then what we have to do is encrypt it and apparently have it reload for some reason. And the way that we're going to encrypt it, we're going to call this encrypt function. We're going to actually have it run, so I have no idea why all of a sudden it's starting to run. But we're going to send the JSON message, that JSON blob, to encrypt. You can see some of the output right now. And then the public key. And what encryption is going to do is it's going to call that encrypt function that the library provides with this message and specify how we want to encrypt it. And I'll talk about this algorithm when I get to the server side. I'm then going to log what that encrypted message looks like. And now the trick is that when we do this encryption, like I said, we're using large numbers, very large prime numbers. And the result is also going to be a number. And the computer, when it works with numbers, when the computer does anything, it uses binary, zeros and ones. Now, that is great for the computer, lousy for all of us. We can't read it, but also lousy for JSON. Remember that there are only a certain number of types that JSON can work with, and binary isn't any of them. So what we need to do is take that binary, whatever it is, it's a bunch of bits, those number of bytes, and turn it into a string. And the way that we do this is with a built-in function to JavaScript, B2A. Binary to, it's actually analog or strings. It's what we usually use for the 8 whenever we have an A. And so what that's going to do is just take that huge series of zeros and ones and turn it into something that it looks like a string, at least. So that way we can share it over JSON. So this is the front end. The other part of this is going to be what we do in the back end. Now the trick is that the backend code, backend.py, this is not particularly interesting. Actually, get rid of these two. Older version. We're going to store all the messages in a database. Our database is going to have two tables, one for public messages, one for private messages. And all of this code, and if you want to look at it, you can. It's not particularly interesting. All it does is just reads, inserts messages as they arrive into the proper database table. And when we need to send a response, reads all the messages from the database table. about the only thing here that might be of remote interest is, since this is input that we got from the user and we will be displaying it in our web pages, note that one thing we have to do before we add any of this to our database is use that function HTML escape to make sure that we don't have an HTML injection attack. So assuming that we've done that, we should be safe. All of the work that we're doing for this encryption stuff, is going to be in main.py. And you can see in order to do this, I needed to use this crypto library. There are a couple packages that we're using. The PyCryptoDome is the package that we're going to talk about today. I also need this package base64. This is what we use to get those, to convert between ASCII text and a bunch of bytes. So when the program begins, we have to do a couple of steps. And it's already actually started. I'm going to reload this just so we can see it. And what I have the program doing right now is each time we start up, right, we need that public key and private key. So I have this function generate keys, which I wrote to do that. And what that's going to do is, if you look, I have the function up here. It's going to start by using that PyCryptoDome library. It's going to call rsa.generate4096. And what this says is generate a new set of public and private keys and have each one of those keys be 4096 bits. So 4096 zeros and ones large. So in human terms, that means that each one, we're going to have two prime numbers, the public key and the private key, each of which is about 1,234 digits long. So you can imagine these are pretty huge numbers. Now, in order to work with it, we do need to create this public key file and private key file. And so what I'm going to do is open up those files. I'm going to first open up my public key file, and I named it public.pem. .pem tends to be the standard name that we use for key files. Actually, not sure I'm sure it stands for something. I don't know off the top of my head, other than the format. Public seems like a good name for the public key. And what I will do is call this function public key.export key and say the format I want, PEM. And that gets the text that we will write out. And then I'll do the same thing with my private key. So if I restart this, you're going to see it's going to take Replit not a tremendously long time, but from a computer's perspective, a very long time to start up. You can see it sort of paused right there because it needed to generate those two 4096 bit long prime numbers. So the next thing I have to do, and this is actually bad practice, it's easy, so I have it right now, but you would never actually want to do this in a real program, is I say, let's read in that private key. Now, in reality, right, we want to keep that private key private. We want to keep it secure. If we keep that private key in memory in a variable, it makes it easier for somebody who's trying to hack our system to be able to find it out. There are ways that if we're running on a computer that's dedicated to our app, it doesn't matter. But when we're running on a shared server, such as Replit, there are ways, while they shouldn't be able to go from one part in Replit to another and hack it, there are ways that can be found out. So ordinarily, we wouldn't want to store this private key in memory where it could be found, but we'll talk about how a better way of doing it. This is the fastest way of doing it. So I'm going to call this read private key to get the private key. And so what that's going to do is open our PEM file, that private.pem file. And it's going to call read to read in the text. And that is, in fact, what you are seeing right here. So you can see what it reads in is not actually a string. It is a thing called an array of bytes, a class bytes. But now those bytes probably look familiar, right? So what I have printed out, so this is the first thing, those class bytes. That is why the B here, we have this B rather than just R or anything else, is to say it should be written or read in terms of bytes, and that avoids issues with new lines. But then the text is begin RSA private key. And you can see we have this huge set of what looks like random garbage. At least, hopefully it looks like random garbage. This is actually the way that RSA is using, it's using ASCII, it's using text to store that 4096 bit long prime number. So this is actually a way of storing a number that's really big, but in a form that's easier for the computer to turn into the zeros and ones that it needs to use. Actually using what we would think of as numbers is actually a little bit harder for it. So that's what the private key is going to look like. But in order to read it, we first have to read in all of that text. We then use RSA to import in that encoded key. And what that's going to give us is this RSA key, right? So I'm printing out what its type is, and you can see its type is kind of weird. It's still not something we could work with. And now that is a big prime number that RSA can use. But there's a last step that we need to do before we can do any of this encryption work. And so the trick is that for encryption work to be possible, there are two things we need to use. The first thing that we need is an encryption algorithm. Here we're using RSA, a public key method. We could also be using a shared key method. There are ways of doing that. All the libraries that we're looking at support both of them. That part's pretty easy. The problem is that different messages will have different lengths, right? If I type hi, or I type the text of War and Peace, when we encrypt it, of course, hi will be relatively small. The text of War and Peace, which is an incredibly long novel, which, to be honest, I have never read, and all I know is it's the example that anybody ever uses when we want to have an example of something that's really long and boring. So we have that text of War and Peace, that would be really long. Because each message would have a different size, that actually would allow Eve to start to figure out information about what's going on. As it turns out, the more information that we leak out, the more that we sort of reveal, the easier it is for people to attack an encryption algorithm. During World War II, in fact, when computers first were being developed, one of the earliest uses of a computer was the Allied forces in Bletchley Park in the UK, led by one of the most famous, we can call him a computer scientist, a really interesting person. Anyway, in the UK, they were attacking Enigma, the German encryption algorithm. And one of the nice things that they had was that the Germans, being Nazis during World War II, they would frequently include the phrase either Heil Hitler or HH in their messages. And because we as the Allies knew this actually gave us a way to hack their systems. So one of the things that we do now is, in addition to encrypting it and having that encryption algorithm, we also specify a protocol that we're going to use to share how the messages are sent. And part of what that protocol does is it makes sure that every message that gets sent is the exact same size. So for longer messages, it will break it up into pieces. And then either for the last message, if it's a longer message, or if it's a shorter message, it actually adds padding, just random garbage at the end, and it has to be somewhat random in order to keep the size perfectly equal. So this last step right here, where I create this priv key variable, what this is doing is this is specifying the protocol that we're using. It's called a protocol. The rules that we're following for each message we send. And in particular, what this protocol does is it says, how do we break up long messages and how do we pad out shorter messages? So once we've read in this private key, now we are up and ready to go. Someone has joined this. Someone has found the link. I actually posted the link. Several people have. I can see public keys occurring. So I can do this too. I have my little thing here. So if we have our web page over here, you can see it being linked up. What's going to happen is they're going to request a public key. And so you can see this is actually the public key that we send them. Again, when we request a public key, in here, we open that public key file, read it in, I'm printing it out. Now we don't need that RB or whatever because this is human readable, and I'm just turning that gobbledygook into a JSON blob. We also can read in the messages when we get a request for messages. What I'm going to do, and you can see here, I got a request for /messages, for /key, for /, that's the web page, /ajax.js, that's the JavaScript file. There are a couple others. The reason why I'm laughing and sort of confused right now is if you look, there's a request for robots.txt. What this means is what actually found this web page and started this getting loaded up is not a student or me. This first query is actually from probably something like Google or a web server. So robots.txt is a file each website can make available to let systems know, like Google, that go out and it's called a web crawler, that go out and search the web and try to find web pages, what pages they should and should not index. So the fact that we got a request for robots.txt means that I guess this page might show up in Google at some point. I have no idea how they found this. I guess it's on my course web page, so that would be it. So somehow Google found the course web page, found a link to this. At any rate, we're going to get all of this. So that part's relatively simple. When we want to get a request for messages, we read in all the public messages, all the private messages, put that all into an object, turn that into a JSON blob, ship it on off. The more interesting thing is what happens when we get a plain text or encrypted message. So to send a message text, I can type in something here. And now let me open up my web console just so we can see what's going on here. You can see the first message I got back, which was empty. If I send this out, you can see that I'm going to send, and since I sent this unencrypted, the blob I sent was just pure plain text. It has the key text, hi class, I missed you, key of null, and of course it receives back exactly what you'd expect. So anything that we send unencrypted is going to be sent unencrypted, received unencrypted, added that way. What's a lot more interesting, and if we look over here, you can see that JSON blob I sent out was also received by the server. That part hopefully is relatively simple. It just calls, right? It sends it to plain text message. Here's my function that posts that. We get the JSON blob, convert it into usable Python data, calling JSON by JSON.loads, get the text message aspect of it, add it to our public messages, and then get a response to send back. What's a lot more interesting is when we send an encrypted message. So I'm trying to think of a message to send. Well, actually, let's do the same message. So I'm going to send the exact same message, but now I'm going to send it using this send encrypted button. So we're going to encrypt it before it goes over. So you can see that here's the plain text message I had. And now on the JavaScript side, right, what we do is we're going to call that this encrypt function, which uses our key, that public key, and encrypts it with that protocol, that OAEP protocol. And then I have it being logged out so we can see what it looks like originally. And so you can see once we encrypt it, we get this thing which can't be read. But one thing to note is it's certainly a lot larger than is needed for hi class, I missed you. Now, the first thing that we have to do, because this obviously isn't text, we couldn't have this work in JSON. So we have to turn it, we use that B2A function to turn it into all of this text, right? And this is just an ASCII encoding of it, a string encoding of that exact thing. And so now if we look on the server side, you can see that's exactly the text. That is the ciphertext that we sent. That is the ciphertext that our server receives. Front main pi, I want the front end, right? So that's what it receives. And we're going to have to use this decoded. We have to turn that bunch of ASCII back into that original bits of zeros and ones that doesn't display very well. So you can see when we call that base64 B64 decode, that gets us a series of bytes. Then, now that we have a bunch of bytes, we can use our private key, right? We sent the public key over, but that private key we can use to decode it. That response that we're going to get is, again, a bunch of bytes. So we have to turn it into a real string, a real str, by calling this decode function. And then, this isn't a great approach to do this, but what I do is I just load in that, convert that JSON blob into regular text. Again, using this constant format isn't always the best idea, but not too bad. And add the private message to our database. So there is a problem with this text and this approach, right? Now note that if I make a small change, actually, before I do that, suppose I say, I don't want to be so emphatic in how much I missed you. I'm just going to use a period here. Note that this is a very small change from what I sent out last time. I'm just changing one character, an exclamation point, to a period. Now, when I send this encrypted message, you can see it received it, no problem. Comes back almost instantaneously. But note that over here we got this whole big long gobbledygook, RH, whatever. Now I get something that is incredibly different than the original message. And this is a really important part of encryption. One of the things that we want to do with encryption is make sure that every change, no matter how small, leads to completely unpredictable results. Ideally, now it's not actually unpredictable, right? There's an algorithm that we're using. It's totally mathematics that we're following here, but we want it to appear to be as random as possible. For those of you who have taken a chemistry or physics class, you may have learned the concept of entropy. That is what we use in encryption. We want the entropy, the randomness or seeming randomness, to be as high as possible because it makes it harder to make any sort of attack on it. Now, truthfully, this isn't particularly secure. Note that the response that we get back is totally in plain text. But it gives you an idea of how all of this works. And any of you could use this right now. Since everything that we do, if you load up this URL, so it's lecture 38A, everything is in lowercase, --profmatthewhz.repl.co. You can use this just as well as I can. And you could, if you were to send a message and I had a way of loading it, I could actually see your message. You can see that there's, right now it's only been me, but you can see that these messages are coming in, that every small change, makes a huge difference. But this is a way that we can actually communicate with the server securely. Now, if we wanted to do so, I would be able to, and I could totally be able to have my client create its own public key and private key and make sure that conversations were encrypted both forwards and backwards. But that honestly wouldn't change too much. It would just be adding the encryption and decryption onto the other side. The idea would still hold. Like I said, since you guys aren't going to be responsible for actually writing a real app that uses all of these libraries, at least in 1.15, I'm not going to worry about that complexity, though the code is always available. I do encourage you guys to play with this. I don't know about all of you. I find this stuff incredibly fun. One of my high points of teaching actually was before I came to UB, there was one semester where I got to teach a course on cryptography, which I absolutely love. Actually, I was one of two instructors. The students came up to me and said, we wanted to take class on cryptography. And I thought, that sounds great. That's a lot of math. I can't do that math. I don't know enough to do it. I love the computer science part of it though. And all those ideas. And they end up approaching, go talk to a friend of mine. I think if any of you have had Dr. Bisson in the bio department, I think it's her husband. Her name might not be Bisson though. I don't remember I only know her husband. But I was like, talk to Terry in the math department, and they talked to him, and he was like, oh, I love that idea. I love the math behind it. I can't do the computers. So we team taught it. It's a really amazing, really fascinating area. I encourage you all to play around with it. It's also really, really hard though. There's lots and lots of math, really fascinating math, just stuff I can't do. I could never derive it. I can follow along, but you get the basic idea. So again, this gives you a quick idea. Just to point out the difference I do have here, suppose that rather than keeping that private key in memory, which is what I originally did, we wanted to do this properly. And the way to do this properly would be each time we want to each time we receive an encrypted message and we want to decrypt it, what we would do is rather than keeping that private key around, we just read it in for that little bit of time, for the bare minimum amount of time that we need it. So suppose that we did this. Let me restart it to use this. It's going to take a little bit because it's got to generate those keys again. There we go. You can see because we're using the same thing, if I reload this, the message is still there. So now if I send the text, it's still almost instantaneous at the moment. It doesn't really add all that much. Though you can see, again, we're getting just even a small change makes a huge difference in what gets sent out. That's the joy of encryption. It doesn't actually add all that much time to do things properly. And this would actually be a lot more secure. So I did want to show you the proper way of doing things. If we wanted to, we could also keep the same keys. In fact, typically, we would not generate a new set of keys every time. Ideally, these last a long time. And actually, we will be showing you this week, next week, depending on how things break out, one of those in the lectures I've referred to how this public key cryptography is used all over the web, how that process works on the web. We'll actually show you some of those. Those don't change much at all. But like I said, that'll be later in the term. So hopefully this gave you a good introduction to how we can use some of these cryptographic libraries, how we can do some of this coding, something a little bit interesting. Any questions about any of this stuff, either on the Python side or the JavaScript side, how we do these secure coding ideas, how encryption works? Okay, I don't see any questions, which is fine. That's good. In that case, thank you all very much. If you have questions about the course or other material or anything like that, please feel free to use Piazza. I actually will have office hours in about 15 minutes, just long enough, honestly, for me to get a bite to eat and use the bathroom. I'm in my house. It's a bathroom. And just be ready. I also have office hours at 4 o'clock today. We'll be talking more about cryptography on Friday. On Friday, what we're going to be looking at is how we can use cryptography and cookies. This idea called cookies, you may have seen them on web pages, that sort of stuff, to actually create a system that you could log into and will be able to follow you around the way that you do on Instagram or Twitter, Facebook, Amazon, any site like that, YouTube, Replit. We'll actually be talking about that process on Friday. So thank you all very much. Stay safe and healthy. Have a little bit of fun. Talk to you all later.